at this point now, I think you are ready to engage with what we call secular functions. So like I said before, I said to engage with these things meaningfully, we needed what we saw before, which was what transformations of function transformations altogether. Horizontal shift, vertical shift, amplitude changes, and all those things. And also the other thing which you needed was about angle measure, which were in this case we've seen what are degrees, and we've taken that from degrees, we've moved to radians. That is now not something we're going to discuss. So now what we're going to do, we're going to look at one function, in this case one trigonometric function, knowledge of which, or this discussion must be sort of transferred to other trigonometric functions, because for me this is the parent trigonometric function. Why do I call it the parent trigonometric function? Because once you've got sine, then you can derive cosine from sine by just taking cosine, meaning sine of the complementary angle. I suppose complementary angles are known, isn't it? And then if you want to move from there, now we've got sine and sine complementary angle, you can then move to tan. And you know tan is a ratio. It's a ratio of sine and the cosine, isn't it? So from there, you can build all the other functions based only on the knowledge of your sine. Actually, I said use the word parent, but I prefer to use the mother function, because mothers are the ones who give birth to things. All together? Okay, good. I mean, it's the nature which is like that, so nobody should complain. Okay. Okay, so we've got the sine function there. Let's have the function in its most simplest and the standard form. We would write it this way: y is equals to sine of t. Now when I'm putting t there, I'm talking about t, radians. It's no longer degrees. Altogether, I'm not going to do t radians. But I think from what we know at school, we dealt with sine function and cosine function as kind of sine dealing with right angle triangles. Altogether, dealing with right angle triangles. But now we want to have sine as a function in order to can define sine for any angle, small angles like acute angles, obtuse angles, angles more than 360 degrees. Now angles more than 2 pi. In that generates as a function. What does it really show? What does it really talk about, this thing? The sine function or the cosine function. Simple. Let's just draw a sketch here of a right angle triangle. Something like that. There's a right angle. Let's put that point there, a point there. Let's say this side here is x and this side here is y. And according to Pythagoras, we know that this length here can be looked at as r, which is square root of a squared plus y squared. And then when we started talking about angles there, we started associating each angle there with a ratio. Like for example, what ratio? For sine, which we are dealing with now, sine of an angle theta, whether it's in degrees or radians, that sine will be what? Y, the length y over r. Now, if we take that kind of a situation and really try to talk about the circular motion, we can take an arm like that. This is your y-axis, this is your x-axis. If you take an arm like that, which is fixed there, at any point here, there is x, y. Whether it's here, there, or there, there's a point x, y. And each one of those points is its own corresponding r. So this ratio here, it doesn't matter whether I deal with r which is equal to 1 or I deal with r which is equal to 4, it will be exactly the same ratio for a fixed angle. Do you understand that? Yeah. Now, if I now take a line which I can rotate like that, at that point I'll give another angle. I'll give a different ratio. At that point I'll give another angle. I'll go to a different ratio. At that point I'll go to another angle, until I'm almost like describing this circular motion. And if you look at these circular motions, you experience them almost every day, in our everyday life. And the engine, when it's moving, it has got a crank, kind of, I think they call it crankshaft. It's moving circular like this, all together. So at every position there, there's a ratio sine and cosine. But as you can see, I think these ratios, they repeat themselves. When they repeat themselves like that, when I come back here, I get the same ratios. When I come back here, I get the same ratios, isn't it? So these ratios, they repeat after every one revolution. All together. Then we say this function is a periodic function. We're going to look at the period later, but let's say it's a periodic function. Something periodic is something like the moon. Every 28 days, we see a piece of it somewhere this side on the west. Okay. So it's a period 28 days. Altogether. I think the period 28 days, sometime this as we see moon, in some people that's a month. When we see the moon there, a month is starting. Not for some people. For me, when I say moon there, a new month is starting. A new month is starting. So standard according to the moon cycle, a month is supposed to be 28 days, not 28 in the quarter days. I don't know who's ever lived that quarter day. But people have got funny beliefs, they can make you believe in anything. So now believe there's a quarter day somewhere in the air. Then after so many years, there's a 1 day extra in the year. You can leave it like that, but I don't know, it doesn't make good common sense anyway. Okay. Even after going to school for many years, it doesn't make good common sense. So just like, are we together, guys? So now you see that function sign now, isn't it? Okay. Now let's do it this way. I'll just take very few examples of this function. Let's consider that this circle, I'll just draw a rough circle here. Let's consider that this circle is what? Is radius 1. But maybe I can remind you of something before I go to this way. Let's go back here. Not really there. There. If that fish line I put around this circle, I take it straight again. Check what is going to happen. I take it straight again. I get a straight line. Infinity going that way, infinity going that way. What can I do now? I can pull this point here and pull it and put it there. After putting there, I take the fish line. Please pay attention. I take the fish line. I take the fish line as if it was rigid and I turn it around this way. Remember what I did? I put the point there and I take the fish line, I turn it around this way until it's horizontal. Then I take that point which was there and I put it there. Then this line goes this way infinity and that line goes that way infinity. What happens? That tells me now the 0 degrees now, I can take it to a real number. Altogether. The radian, which was radian there, is now on the line here as a real number. Altogether. What is he saying? He's saying that our angles now are going to be measured using real numbers. Altogether. Did you hear that? Good. If you heard that, very good. All together, guys. Okay. So let's move forward to the way we were. We're here. Let's say now, using that, let's play around with that kind of a small circle which I drawn there. It's radius 1. Now I'm going to say this point here, the angle here, is half pi. The angle here is 0. The angle here is pi. The angle here is 3/2 of pi. Oh, sorry. 3/2 of pi. Do you agree with that? Okay. Now, let's go to that situation where we said sine t, replacing that theta, is equals to what? Is equals to y over r. But what is our r in this case? It's 1, isn't it? Then if r is equal to 1, then this thing lands us here. All together? Okay. Now, at this point here, the angle is 0. So we're saying sine of 0. Now we are on the y-axis. What is the coordinate y? 0. So this thing is going to give us 0 over 1, which is going to say that this is 0. All together? So now, let's just do something here. Let's draw, oh no, that is bad. Let me draw a line here. All together? Okay, let's make that line, and then this is our x-axis and this is our y-axis. Now I want to plot these points now. What is happening here? Here, the point is, the angle in radians is 0. The value y of the function is 0. Do you agree with me? So the point is there. But first of all, maybe let me divide this thing equally. 1, 2, 3, 4. I'll call that. Is it 4 there? No. 1, 2, 3, 4. I'll call that pi. We say our pi is there. Then 5, 6, 7, 8. I'll call that 2 pi. Remember, these are angles. These are real numbers. All together, guys. Okay. Now this point here, which is 0 radians, is giving us 0. So we've got a point there. Then let's go to the next one. Let's come to this one. This is half pi, isn't it? Okay. Now at that point there, the radius is 1. If now we come to this kind of situation, this radius is 1, and what else do you want? We want x there. Sorry, what do you want? We want the coordinate y. What's the coordinate 1 there? It's 1, isn't it? So when we define the angle, it will be 1 over r. What is r? 1. Which means now, at half pi, which sits here, the coordinates of the points will be what? Will be t is equals to half pi, and the sine ratio is what? 1. Then we need to measure 1 here. We need to get 1 here. Let's take 1 which is reasonably good here. The scale does not need to be the same. We can choose our own scale here, another scale here for 1. Let's count it here. 1, 2. Let's get that thing there as our 1 on this axis. And then we count the same number. 1, 2. We get this one. Is it? Am I right there? Check that for me. Or there. Then that will be what? Minus 1. So this point is a point which is half pi and the 1. It must be there. All together. Okay. Then we come to this point here, which is pi. The radius is still 1, and the y-axis is what? The y-axis is right on the this point is right on the x-axis. What is y-axis? 0. So we're going to have another 0 over 1. So we're going to have now what? We're going to have pi, comma, 0. So the s coordinate will be pi, the horizontal coordinate will be pi, and that one will be 0. So which means now the graph cuts through there. Altogether. Then, after that, we come to this one, 3/2 of pi. What is the y-coordinate? Here. What is the y-coordinate here? -1, is it? And the radius is 1. So which means it's going to be -1, is it? So which means at this point where we've got 3/2, this function is going to be -1. Then we come to pi. What did we say? We say this function repeats itself every 1 revolution, which is 2 pi, is it? So actually what I was saying, they were saying is period 2 pi. So after 2 pi, we expect it to give us the value which is there. Let's look at 2 pi. It's exactly the same point. The coordinate y is 0, and that. So get that y there. Roughly now, we are ready to draw our function, guys. What's going to happen? That color is red, ne? Is it red? I don't see it properly here. So now it's going to be function going like that. Up, down, up. Oh, sorry. There's a mistake there. You see it? Okay. What did I do? Turned up N, isn't it? That is the function. And that, from 0 to pi, we're going to call that the principal period of the function. All together? Okay. What I want to highlight to you here, very, very important things, is the turning point. You must check that the turning point here occurs when t is equals to half pi, and also when t is equals to 3/2 of pi. It looks like it. These halves of pi, this function is going to have a turning point, is it? Okay. Then the zeros, I said they're turning points. Then it also highlight zeros. Where are the zeros? I'm looking at those points where the y-coordinate is 0. We call them zeros. But we look them in terms of t. When does it occur in terms of t? It occurs at t equals to 0. And also at t equals to pi. And also at t equals to 2 pi. So within one period, which you can also say within one cycle, it has got 3 zeros and the 2 turning points. That is very important to note. How are you guys? That is the sine function. Let me tell you something now. At this point now, we are ready to play around with the sine function in terms of its transformations, multiplying the variable t, subtracting or adding something to t, multiplying the function's itself sine with a number, amplitude. So we are able now to play with what? With the variable, with the amplitude, and the horizontal shifts and the vertical shifts altogether. But please guys, listen, if you're not aware what is the turning point of this function, if you are not aware of this, if you don't see the standard graph of the function, the shape of the standard graph of the function, please tell me, which means you don't understand this far. You must understand how we call that standard graph of the function, and that standard graph is the one which is going to control us when we play around with the transformations of this function. Altogether. So let's knock this into a system. Knock it into a system. Where are the zeros? Where are the turning points? The shape of the graph. Altogether. And we know, what does the graph describe? It describes circular motion. Altogether. Circular motion which involves angles. Angles now which we are going to measure using 2 different units. Either using degrees or radians, where it's possible. All together, guys. Can I move forward? Okay, let's move forward. Now, we will part from here and say, this is the standard graph of sine. Basically, I will put this as 0 for initial point. The next thing what I'm going to do is to to this and say A sine t. Now, if you want to check what this A sine t is going to do, check what A did to the parabola when it was greater than 1. The function was lifted up altogether, which means the function is going to make upper, higher waves altogether. When A is smaller, the function is going to fall down. Now it's going to come closer to the horizontal axis. That is very important altogether. So monitor, first thing here, monitor the effect of A. And that A is called the amplitude. Already when we're talking about the parabola, we talked about the amplitude. That angle is equal to amplitude. At this moment, you must imagine how the graph is going to look like in relation to the previous one. Because look here. A here is precisely 1. Now if A was 2, this point will go up there, isn't it? Now we must see how the two graphs reflect. Listen guys, you are going to be asked in test or exam to engage with this and say exactly the accurate information about what has happened to the graph. So please don't ignore it. Good. The next thing. This is 1. Then we go to 2, second step. Initial step, step number 1, second step now. Then A. We now know the effect of A. We now have sine. And then now we've got 2. I love 2. Altogether. What happens there? But I didn't want to put 2 at the moment. I think it's not good to put 2 at the moment because now I'm choosing a very funny thing, particular thing there. What I'm going to do there, I'm going to put omega t. So omega could be 2, could be 3, could be 4. Is that right? Okay. Then now omega is going to be called, that's not an equal sign. I put 2 dots then equal. Yeah. They normally we use this thing to say by definition this omega is what you call angular velocity. Altogether, the angular velocity. Then after this, you see this, I'm not just multiplying the variable. Okay guys, I think what we can do now, I'm going to stop here because the time is not allowing us. So I'm going to stop here and say this is how far we've gone. We're going to continue from here. Then we're going to explore further and do practical examples of all the effects of these parameters we've changed here. Then we'll say we understand the sine function. Then we'll see how we can transpose that to other trigonometric functions. Thank you for listening.